Okay, welcome. Hey, Susan, Caesar, and Bradley, and Ralph, and Jordan, and Victor. This is yet another linear algebra day, but today's kind of a special day because today is mostly applications. So we're going to kind of see how linear algebra is used in some different ways, and hopefully it'll make sense to you. Some that you've heard of before and you've never thought of them as linear algebra, at least one of them. So we'll take a look. So let me share my desktop. And let me tell you the plan of the day. So we'll start out as usual. I'll answer any questions if you have a homework problem or whatever you have questions on. And then we'll talk about steady state vectors. And the idea is that a matrix is, again, it's a linear transformation, a function on vectors. And the question is, if you apply that function to a vector, will you ever not change a vector other than zero? Zero never gets changed. And that's a good question. And we'll talk about steady state vectors. Then we'll look at population over long periods. And that could be long as in infinity. It could be long as in 10. All depends on what we're looking at. We'll look at dynamical systems. And that has to do with when you have a sequence of events. So kind of one of the common ones is annual. So is there anything that happens annually in nature or physics?
Seasonal change?
In nature, seasonal change, yeah.
Yeah, seasonal changes happen. Population growth is not for all species, but some species is an annual thing.
Yeah, with breeding seasons and things like that.
Yeah, a lot of species only breed, they only breed and have their little ones in the spring. So it's not the kind of equation that you see in calculus, because if it's only once a year, you can't take limits, right? You can't look at 1/10 of a year because a 10th of a year doesn't matter. And we'll look at these discrete dynamical systems. And then we'll pick a very specific one, which is called the Lotka-Volterra system. Have you had that before or heard of it?
I haven't.
I've heard of latkes before.
This is not the same. No, these are people. Okay. People a little bit after World War II. And they ended up finding something that they didn't believe. And it turned out that, good news, they were mathematicians and they were able to realize why it was happening. And now there's a whole system for it. And I'll talk about that. And then comes the Fibonacci sequence, or the Fibonacci numbers. Have you heard of them?
Yeah.
Yeah.
Okay. So what is the 10,000th Fibonacci number?
No idea.
Okay. Do you think you could figure it out?
Eventually.
Okay. Eventually. So there's two choices. One is you can sit there working on paper the way you know how to maybe do it now. And I don't think you'd eventually do it. I think you'd give up. Trust me, it would be miserable to do it that way. Or you could use linear algebra. So instead of taking, a year of writing and giving up, instead, spend 10 minutes and finish it. And that's the good news, is that you can do that with linear algebra. And we'll understand that pretty well. And then we'll have e to the a, which seems a little weird. And I talked about it last time, but now I'll actually formally define it, because what does it mean to take e to a matrix? And it turns out it does mean something. And we'll do that, and it'll be involved power series. And then we'll use e to the a to be able to solve initial value problems. So last year, so in calculus, you did things like, I don't know, y prime equals 4y. Do you remember how to solve that? Hadn't been that long.
You integrate both sides, yeah?
Not quite at the beginning. There's one step you have to do first. Or possibly two, however you look at it. Remember, you write it as dy over dx equals 4y. You divide by y and you get dy over y equals 4. And then you integrate both sides. Does that ring a bell at all?
Oh yeah, you have to convert it to Leibniz notation, and then yeah, okay.
Yeah, I promised it happened. It really did. Okay, and you got through it when you took second quarter calculus. And
that was before the quarantine even. Oh my goodness.
Wow. Yeah, it was before the quarantine. I know. It's like we have no memory of anything that happened before quarantine, but it really did happen. So, you could do that, and that sounds great. But what if instead of y prime equals 4y, what if you had two variables instead of one variable? Let's suppose you have x of t and y of t. And instead of y prime equals 4y, let's suppose you had, I don't know, say x prime equals 3x plus 5 and y prime equals 2x minus 6y. Can you solve that? And the answer is yes with linear algebra. So we'll see how to do that. And it'll involve e to the a, by the way. Any questions on what we're planning on doing today or on the homework or anything else?
I have a quick question. If matrices are functions, can you take derivatives of them?
Sure. Yeah, it turns out that taking a derivative of a matrix is easy because you take it component-wise. Kind of like adding two matrices is easy, right? So you just take the derivative of all of the elements, and that's the derivative.
Okay.
So sorry if I, ruined your day because it's not that exciting, but it's easy. Do you understand what I'm talking about?
Yeah, it makes sense.
Yeah. Okay, other questions?
Yeah, I have one about Markov matrices actually. It's more of a general thing, but I don't quite understand why when we're trying to figure out how a population is changed after a single time period, we just multiply by the whole matrix. Wouldn't it make sense to multiply by one of the columns instead, since those are the probabilities over a time period, over distances in time? Or am I misunderstanding everything?
Yeah, I think the easiest is for me to write down an example. Otherwise, I think it's too theoretical talking. So if we have a matrix, so let me pop in, just going to randomly grab a matrix. That's a Markov matrix. So let's suppose you have, I don't know, how about 0.3, oops, 0.3, 0.7, 0.9, 0.1. Do you agree those are that's a Markov matrix?
Yeah.
Okay. So what that does is it tells you what it's doing to an XY. That's what a Markov matrix is all about. So yeah, you have the 0.3 and 0.7. You have the 0.9 and 0.1. That's true. And those are important, the two columns. But you need the whole matrix to understand what it does to XY. So let's look at it. Let me pop in an XY. Always takes a minute to draw them. Whoops. Okay. So a Markov matrix is a function that applies to a vector. Does that make sense?
Oh, so it's like a linear transformation then.
Yeah, it's not even like one. It is a linear transformation, right? With a special property in that the sum of the columns are all zero, all one, and the entries are all non-negative. Does that make some sense?
Yeah.
And what it does is it says, well, if we start out with an XY, where is the next item? Well, the next item is, by definition, you multiply. And if I multiply, I get 0.3x plus 0.59y. And then if I multiply, if I keep multiplying, I get 0.7x plus 0.1y. So does that clarify things completely?
Yeah, that makes a lot more sense now.
Yeah. And if
I guess I wasn't really conceptualizing it as a linear transformation.
Yeah, it really is a linear transformation. So the idea is if I give you an XY, you plug it in and that's what you get. Does that make sense?
Yeah.
And if you plug in an XY, you get some numbers, right? And then if I wanted to say, well, what if I did it twice? Well, then you do it again. Does that make sense? And you can do it 3 times or 4 times or 10 times. But one of the nice things about Markov matrices is, what do you know about the eigenvalue?
It's 1.
Yeah.
Well, one of them is 1 at least.
Yeah, one of the eigenvalues is 1, and that makes it much nicer if you're trying to find an eigenvector. Does that make sense? Because then you don't have to find the characteristic polynomial at all. You know it. Is that clear?
Yeah.
Okay. Other questions? That was a good question. Important one. Other questions? It's a quiet group. Okay, if there's no more questions, I guess I'll talk about some steady state vectors, and we'll do some examples. And the way I write it, sometimes I differ from the book in certain ways. When I read through the book and then make my notes. And they call it a theorem. I call it a theorem / definition, because while they state the theorem, they also define something. So here's the theorem / definition, like the way I call it. And that is, let A be a Markov matrix. So here's above an example of a Markov matrix. So you answered a great question, because now we've gotten to remind ourselves what a Markov matrix is. So let's suppose that A is a Markov matrix. Then there exists a steady state vector V sub s, such that V sub s has positive entries that sum to the same values as the entries of V naught. And AV sub s equals V sub s. And then note that this means that 1 is always an eigenvalue of A. Any questions on the theorem / definition? Okay, so it's a definition because we have these new words called steady state vector. And it's a theorem because we say that 1 is always an eigenvalue. And I mentioned it. We haven't proven that yet, but it's not too hard and we'll get there. So 1 is always an eigenvalue of A. And we know that AVS equals VS. Okay, and that's immediate once you know 1 is an eigenvalue, by the way. All right, well, it turns out the proof of this is interesting. You know, if I asked you to prove this, like a lot of these, you probably would have no idea. Am I right? Maybe I'm wrong. And any ideas? Okay, the idea here is You don't look at A. That's why this is a tricky one. But once you come up with the trick, it's pretty easy. You look at A transpose. So the proof is look at A transpose. All right, now do you remember the difference between the eigenvalues of A and the eigenvalues of A transpose?
Aren't they the reciprocal?
No, they weren't the reciprocal. The hint is easier.
They're the same.
They're the same. We had a theorem about that. Do you remember the theorem? I know. 2 days is an amazing amount of time, isn't it? So the theorem that's going to have, so if we show that 1 is an eigenvalue of A, then 1 is an eigenvalue of A transpose. Does that make sense? And vice versa. If we show that 1 is an eigenvalue of A transpose, then 1 is an eigenvalue of A. So now let's do it. And hopefully you remember how to do it. You write the determinant of what?
A minus lambda I.
Except I'm going to write A transpose because that was the trick. A transpose minus lambda I. And actually, I'm just going to look at I because I want to prove that if I plug in 1 for lambda, that I'll be in good shape. Does that make sense? Well, why must that be 0?
Because it sums to the same value as the entries of V0?
Yeah. So we know, so subtracting I as a sum isn't going to change anything when you add up the rows. Does that make sense? So what do the rows all add up to?
One.
Except we subtracted I. That's the key.
0.
So they all add up to 0. Do you agree? Because the rows of A transpose add up to 1. And then if you subtract I, then at every row you're subtracting a 1 from one of those entries. Do you see? The first row, you're subtracting 1 from the first entry. Second row, you're subtracting 1 from the second entry. But the point is, when you add up all of the entries, you've only subtracted 1 at one time. Okay, well, if the rows all add up to 0, what do we know about the determinant?
Must be 0.
Yeah, the determinant must be 0. Okay, I guess not the determinant have rows, but A transpose minus I has rows. Right, determinant's a number, doesn't have rows. So let's write that down. A transpose minus I, and I guess better is has. It's a matrix. Has rows, and all the rows add up to 0. So therefore, the determinant is 0. Any questions on that? And if the determinant is 0, that means that we're in good shape. That means that 1 must have been an eigenvalue of A. And what does it mean that 1 is an eigenvalue of A?
It means it's a Markov matrix, right?
Actually, we started with a Markov matrix. It doesn't mean it's a Markov matrix.
that's just one thing that Markov matrices have.
Right, but you could have a matrix that's not a Markov matrix, where 1 is an eigenvalue of A. Okay, that you could have actually.
Diagonizable. No?
Yeah, but what do you know about that? What it means is that the following right here. There's a vector V such that AV equals 1 times V. That's what it means to have an eigenvalue of 1, right? Call that VV sub S. It's always fine to stick a subscript. And we're done. So that means every Markov matrix has a steady state vector. Any questions on that? Okay, so that means that there is a vector that doesn't move when you apply the Markov matrix to it.
It stays the same.
Yeah. So, right. So for example, if you have a Markov matrix that kind of represents remember the population example I gave a couple days ago? How people are going from one state to another state? California, Nevada, and Arizona. What it says is that there's going to be a specific vector or a specific number in California, number in Nevada, and number in Arizona. If you wait till next year, how is it going to change?
It won't.
And how about the year after?
It still won't.
How about the year after that?
Still won't.
It's going to get kind of boring, right? Okay. And that's what happens. So when you have a Markov matrix, there's always at least one vector that just hangs out every time you apply A to it.
Can there be more than one?
Sure. Here's an obvious example. What's the easiest Markov matrix there is?
Just the letter 1. I mean, what am I saying? The number 1, just one of them.
Yeah, so number 1, but in our class, we really don't do 1-by-1 matrices. How about the easiest 5-by-5 Markov matrix?
The identity?
Yeah, the identity, right? Do y'all agree that the columns of the identity all add up to 1?
Yeah.
Right? Now, are there steady state vectors? Can you think of a vector such that the identity times the vector is the vector you started with? What do you think?
Yeah, any vector, right?
Yeah, any vector, right? So the identity is an example of a Markov matrix where every vector is a steady state vector. Okay, people usually don't talk about the identity because it's so easy and it's not that interesting as a Markov matrix because nobody cares. Does that make sense? No one cares. You know, the identity is sure, but you don't spend a lot of time studying the identity because there's nothing to do. Okay, but for other matrices, so sometimes you can have a single vector, sometimes you can have more than one vector. Any questions on this theorem/definition? Hopefully I didn't blow you away on it, but it's a nice theorem. So that means that we can always just say that if you have a Markov matrix and you're looking for an eigenvalue, just look for 1, because 1 will always work. Any questions on that? Okay. So find the steady state vector for 0.7, 0.6, 0.3, 0.6, 0.7, 0.4. Do you agree that's a Markov matrix? I'll let you look at it.
Yes, I agree.
Yeah, if you understand Markov matrices, you should be able to say it within a couple seconds. And V naught is equal to 200, 500. So you can kind of think of this again is that if you start out with 200 people in California and 500 people in Nevada, and then you wait till the next year or whatever, then you're going to end up with 0.3 times 200 plus 0.6 times 500 people in California, and 0.7 times 200 plus 0.4 times 500 people in Nevada. Any questions on that? All right, so here's an example, and this is one I want you to try, is let's see if you can tell me a steady state vector, in this case, the steady state vector, for this situation, and round to the nearest whole number, because you're going to get some, you get an ugly decimal. So round to the nearest whole number. Okay, by the way, is there a solution to this? Is there a steady state vector? Before you do anything. Might you just end up giving up because there just isn't one?
It's a Markov matrix, so it needs to have a steady state vector.
Yeah, so the answer is yes, there is a steady state vector. You have to be, there is a way of doing it. I'm going to give you a few minutes to try. Let's see if you can find the steady state vector for this matrix vector combination. And again, round to the nearest whole numbers. And I'll give you a few minutes. If you have questions, you can ask. And when you got it, put it in the chat box. Type the 2 numbers. It's a vector. And it's a vector in R2. And again, if you're stuck, ask a question.
I think I'm stuck, actually.
From the beginning or from the end?
It's like near the middle, essentially. Like I got the matrix from like subtracting I and A, 0.3, 0.6, that matrix. And I got the equations from it, but then I try solving and I can't get, I don't know how to proceed from there.
Okay, anyone else? It's been a little longer than I expected, so maybe I'll go over it. So it isn't that bad, but it's only not that bad if you watch me do it. You know how that is, right? So
well,
do I need to find the determinant of a minus lambda I and then find, get that characteristic polynomial, solve the quadratic? Do I need to do that?
I don't think so.
Right. I don't need to. Why don't I need to?
We already know one eigenvalue.
Yeah, we know the eigenvalue, the important one. We know 1 is an eigenvalue. So immediately, the fact that this is a Markov matrix, that means that if I want to find the steady state vector, I know 1 is an eigenvalue, and I just want the eigenvector that corresponds to 1. So what I can do is I can take the matrix and subtract I. And when I do that, 0.3 minus I is negative 0.7. And remember that because 1 is an eigen value, bottom row doesn't matter. It's just 0, 0. Any questions on that? Any questions? Okay, so now I just need to find the null space of this. And to do that, I need to next to RREF, there's one more step, and I think I'm going to go for it. I'm going to divide by negative 0.7. And that makes this a 1. And it makes this a negative 6/7. Any questions on that step? Have I done anything hard yet?
No.
Okay. Nothing I'll do is hard, but you know how it is. The hard part is knowing to do it, not necessarily doing it. Okay, so now let again, this isn't going to be the right answer, but it'll get me to the right answer eventually. And that is, now let's find an eigenvector associated with the eigenvalue 1. So let me set it up. There we go. Okay, just to make life easy, what can I let, by the way, what's the free variable?
Y.
Y is a free variable. So what's a good number to let Y be?
7.
Yeah, let's Y be 7. So if I let Y be 7, what's X?
6.
6. Okay, actually, yeah, X is 6. Okay. So that is, is that a steady, is that the steady state vector?
No.
Why not?
It doesn't sum to 700.
Exactly. It needs to sum to 700. Okay, what does it sum to?
13.
It sums to 13.
So what do I have to do?
Find a way to express that ratio in a way that it adds up to 700.
Yeah, so I multiply by 700 over 13. Was that easy? At least easy to think about?
Yeah, that makes sense.
Okay, so that might have been where you got stuck. I'm not sure. You know, it's hard for me to know. So I'm going to multiply by 700 over 13. And I'm going to multiply by 700 over 13. Any questions on that? Okay, now the rest, I didn't expect you to do this by hand, by the way. I mean, you can. You know, you could take 4,200 and divide by 13 by hand using long division. But I think you're wasting your time. What do you guys think? Do you agree?
Yeah.
Yeah.
So I can't do that. I could do it in my head. It'll take a long time to do my head. But what is 4,200 over 13 rounded to the nearest whole number?
323.
323. Good. And what is 4,900 over 13 rounded to the nearest whole number?
377.
377. So there's our steady state vector rounded to the nearest whole numbers for this Markov matrix and this V naught. Any questions? Any questions on how to do this? So wherever you got stuck, when you look at it now, is it a lot easier than you were making it?
Yeah.
Yeah, for sure.
Yeah. One of the main things to note is that when you find an eigenvector, you found one example of an eigenvector. And if it's dimension 1, all examples are constant multiples of that eigenvector. Does that make sense? So pretty much I said, I need to add to 700. I add to 13. So I need to multiply by something that makes it add to 700. 700 over 13. Makes it work. Any questions on that? Okay, and multiplying by a constant is always okay as long as the constant's non-zero to get an eigenvector. Any questions on this example? So that's a steady state vector. Okay, now comes a discrete dynamical system. And this is what I was saying about a lot of biological systems, especially, and others too. A lot of biological systems are discrete systems because, for example, bursts of, I don't know, stellar jays. Okay, how often do they nest and lay eggs?
Once a year.
They only nest once a year. Okay, I know because they're always nesting at my house. Okay, I don't know if they nest at your place, but they nest at my place, and it's once a year, and it's every year, and they have a certain number of little chicks. So there's a lot of biological organisms where it's an annual thing. Okay, what else might be discrete besides biological reproduction?
I was thinking like economic situations.
Yeah, there's definitely economic situations. For example, if you're looking at company profits, then yeah, the profits might be pretty continuous, but you'll never find continuous data, right? How often does anyone know how often does a company report their data?
It's usually like annually.
Nope. No, annually they if they sell if you could buy their stock, let's call it that way. So bigger companies.
Quarterly?
Quarterly,
Yeah,
isn't
quarterly.
it? Like,
Yeah, quarterly is an American law. I don't know about other countries, but in America, they have to submit a quarterly report. So in that case, you would do a discrete system. Does that make sense? Okay. Where else besides economics? So I can pretty
maybe
much.
elections.
Okay, definitely elections and election systems. And I don't know if I ever told you this, but not this last election, but the one before that, the Democratic contender, the person who won the Democratic primary, won because of me personally. Okay, in our district. Okay, do you know what I did in one word?
Voted.
Math.
Oh.
I did math, and I showed the Democratic Party that they made a mistake. Okay, and it was this kind of system. It was too complex to explain in class, but it involves statistics and linear algebra. And they didn't do it right, and I showed them their mistake. It wasn't on purpose their mistake or anything, but they weren't mathematicians, and they said, "Oh, can you help us?" And I helped, and then the person won because that person got the support of the Democratic Party. So it really does matter. Okay, and that can happen every 2 years, every 4 years, every 6 years, depending on what the system is. Does that make sense? Okay, how about physics? Is there anything discrete in physics?
I was thinking like moon phases, like eclipses.
Eclipses are pretty much not discrete.
Periodic motion.
They're only discrete because we're looking at it. But now the moon phases pretty much keeps going. Just you have to be in a different place. Peg motion, that's not discrete either. That's continuous. Quantum physics is discrete, right? Either that electron appears or the electron doesn't appear. Does that make sense?
Yeah.
It's an all or nothing, and discretes are all or nothing. Okay, it doesn't slowly change. It's like bam, you have an electron. It's not like you have a third of an electron and then you have a half an electron. You have 2/3. It doesn't work that way. You have nothing and you have something. And so definitely that's a discrete dynamical system. Okay, so that's physics. Pretty much in every field, but not in every application, but every field, there's a discrete dynamical system. Okay. For our class, remember, what's the name of our class? And don't say 203.
Linear
Linear
algebra.
algebra.
Linear algebra. So for our class, we're going to assume that it's linear. Okay. So that means that this discrete function that tells you how to go from the nth state to the n plus first state will be determined by a matrix. Any questions on that? So that means vk plus 1 equals a times vk. And that's a discrete dynamical system. Any questions on that idea? Okay, by the way, again, our class is linear algebra. Are there examples that are not linear? Do you think there are?
Yeah.
Oh, yeah. Yeah, most examples are not linear. Okay, but it turns out if it's not linear, you're probably not going to be able to solve it. Just to let you know that. So if it's not linear, you can't solve it, but you can solve it using, you can approximate it. How do you think you approximate it?
Using a computer
Yeah, but mathematically.
with linear algebra.
No, that's what you want to get to linear algebra. How do you get there? Use tangent planes. So a tangent plane, and that's in 3D, a tangent plane in 3D approximates linearly a discrete dynamical system that is not necessarily linear. And as long as everything is smooth, which is true in most cases, as long as everything is smooth, then if you don't go too far away from the point that you know about, then it works pretty well. So usually you usually use linear discrete dynamical systems to solve discrete dynamical systems. And sometimes you do it in stages. So what you do is you basically look at that surface, you look at a tangent plane, you move a little bit, and then you get to the tangent plane after you've moved a little bit and do draw a new tangent plane. Then you move a little bit and you keep going. Okay. Do you know what that's called? I've mentioned it. I don't know if Bruce has also. And it's done in a big way in artificial intelligence, but other things too. Do you remember what that's called? It's called gradient descent or gradient ascent, depending whether you're going up or down. I don't know if you remember those words, but that's what that is. And if you're going to use gradient descent, then that means that you're going to do a discrete dynamical system. You're going to linearize it and write it as a vk plus 1 equals avk. And then you're going to do that. You're going to apply it a little bit, and then you're going to do it again and again and again and again. Any questions on this idea? All right, so here's an example. Here's a biological example. I tend to pick the bio examples because they're easiest for everyone to like relate to. Hopefully you can. And I tried to pick some something that you might know. Do y'all know what a vole is?
It's a little rodent.
Yeah. And what most people don't know, most people think dogs are like what coyotes really eat all the time. That's what they can, but they don't eat that many dogs. Their main food is voles. Does that make sense? So here's an example. So suppose the number of voles the following year will be equal to twice the number of voles the current year minus 90 times the number of coyotes the current year. Does that make sense? That if you have a lot of voles, they're going to reproduce and get more voles. Okay. On the other hand, if there's coyotes around, they're going to eat the voles and the voles are going to die. Does that make sense? And coyotes eat a lot of voles, not just one. Okay. And the number of coyotes next year will be equal to 0.01 times the number of voles. Again, if there's no voles, the coyotes are going to die out. Okay. But they need to eat a lot of voles. That's why it's 0.01. The current year plus half the number of coyotes the current year. The more coyotes there's going to be, but they need voles also. Okay, this year, there are 20,000 voles and 50 coyotes in an ecosystem. Okay, any question on the scenario? Okay, so we have two parts. Let's do part A first. Oh, you know what? I want to go this way. I want to be a new page. There we go. Okay, so first part is how many voles and coyotes will there be next year? How do we figure that out?
Create a Markov matrix to represent the situation.
You have the right idea, but not quite right. It won't be a Markov matrix. Okay, it's not a Markov matrix, but it'll be a matrix. So let's create a matrix to deal with the situation. Okay, it's not a Markov matrix because if you have the right situation, you can end up with more of both. Does that make sense? And similarly, if you have the wrong situation, you can have fewer of both. Whereas with Markov situations, that doesn't happen. So this is not going to be a Markov matrix, but we can write down this as a matrix equation. And then next year, it'll just be the matrix times our vector. So let's look at our matrix. So first thing, what's the dimension of the matrix going to be?
2 by 2.
Yeah, this one's going to be a 2 by 2 because there's voles and coyotes and they depend on each other. Okay, voles hate coyotes, coyotes love voles. Okay, what's going to be the first entry? And we'll let vole be the first variable and coyote be the second, by the way. It won't be 20,000. That's not going to be the matrix. That's not part of the matrix. It's going to be important, but not part of our matrix. The hint is read the first sentence. And even the very first part of the sentence. Not just word suppose.
0.90 or?
No. The hint is it's not a number you can see, but it implies a number. That's a hint. Read the beginning.
It's going to be V, like it's going to be a variable.
No, it's going to be a number.
Oh.
But the hint is it's given as a word, not as a number in the question.
2.
2, there we go. Because 2 means that for that first entry means that next year, there'll be twice the number of voles to start out, if you don't worry about coyotes. Do you see that? So it's going to be 2 times the number of voles. Any questions on that? Okay, what's going to be the first row, second column entry?
-90.
Yeah, -90, because for the number of voles, you're going to subtract 90 times the number of coyotes. Any questions on this? Okay, what about the second row, first column?
0.01.
Good. Any questions on that? And how about the last entry, second column, second row?
1/2.
Yep, that's going to be 1/2, or let's try this 0.5. Okay, any questions on that? All right, how do we come up with how many there's going to be next year? Here's a hint. What haven't we used yet?
The 20,050.
Right. If you don't know how many there is this year, you'll never know how many there are next year. Does that make sense? So how do I use it?
Write it as a column vector.
Yeah, I multiply the matrix times the vector 20,000, 50. So let's put that in. Any questions on that? All right, I'm going to let you do this. Tell me what you get. And by the way, you don't have to do it by hand. You can, but you don't. It's not necessary. But it's not too hard. Okay. Oh, good. I love it when you agree. So 35,500. That's what I do when I get it in my head. That's what I got too. And 225. All right. Who did better, the Bulls or the Coyotes, by the way?
The Bulls.
It all depends on how you look at it. Okay. So the voles, we got a whole lot more voles, but they didn't even double in population. Coyotes more than quadrupled in population. Do you see that? But really, they're both happy, the voles and the coyotes. Any questions on that? All right. How many voles and coyotes will there be 5 years from now? So how do we do that?
We use the results we just got and do it again.
That won't be 5 years from now if we just do it again.
Well, we got to keep doing it. The next result will do that as well.
Okay, so that's true. We got to keep doing it. Or, remember, you're allowed to use calculators. What can I do calculator-wise?
To the 5th power?
Yeah, I can take it to the 5th power. Because doing it over and over and over again means taking the matrix to the 5th power and then multiplying by 20,050. Okay, and again, Symbolab can do this. Let's see if you can do it. Pop it in your computer. And so can other computer systems. I just pick on Symbolab because it's easy. All right. So I'm going to round to the nearest whole number since we're talking animals here. So 17,436 and 1,004. So by the way, we're looking at a situation where if you just wait, it's just the whole world is going to be overrun by voles and coyotes. What do you think?
No, it doesn't look like that.
Okay. What's happening? Are you going to be overrun by voles or coyotes? One of them? Neither of them?
Probably neither.
Yeah.
Right. I mean, look at the coyotes. What happened to the coyotes?
They're increasing.
So are they going to keep increasing forever?
No.
No.
Why not?
Because they're gonna run out of voles to eat.
Exactly. Exactly. And in fact, if you keep doing this, in fact, you try it, try it. Since if you put it in symbol of it, it's really easy to change the 5 to a, you know, a 9 or a 6 or a 10. See what you get.
Is this how things like carrying capacity are determined?
This is, well, you could do models to find carrying capacity, but this is not quite how carrying capacity is done. Carrying capacity is done by looking at the model and then taking a limit as t goes to infinity on the model.
Okay.
And then assuming that as t goes to infinity, if it hangs out at the same, then that's the carrying capacity. This is a little different. So what's going to happen here?
So I did 20 years, and I got a negative number for voles, and then like 190,000 for coyotes, which wouldn't make any sense at all.
Okay, so if there's negative, right? So then you could think about it. As soon as you get a negative number for voles, what happened? What's happening?
There's no more voles.
There's no more voles. And then you got to remodel. This is very important about modeling. Then you got to reset your model and say, now we have no voles. Does that make sense? So that negative becomes a 0. Well, as soon as the voles is a 0, then the voles are always going to be a 0, period. Does that make sense?
Yeah.
Well, as soon as the voles are a 0, then you can go back and now you can use first year calc. Because the voles are gone, the coyotes, you're only going to get a half the number of coyotes each next year. Does that make sense? Right? Why might there still be some coyotes if there's no voles?
There's other food.
Other food
Yeah.
sources?
Any of you guys have like dogs or cats that you let outside?
Yeah, and they never came home.
Yeah, that's because the coyotes have to eat because there's not enough voles for them.
My mom told me I went to a farm.
Yeah, right. Okay. Yeah, it's called the coyote farm. Okay. And what's going to happen is you change the model, and now you're talking about a half power model. So now you have exponential decay in coyotes, and the coyotes go extinct too. And what you can end up happening, there's all kinds of different situations with these matrices. You could have that situation where they just both go extinct. You could have the situation where they both jettison to infinity. Okay. And of course, that can't be real because you can never get an infinity number of species. But you could also have a cyclical pattern. Eigenvalues and eigenvectors, when do you think you might have a cyclical pattern? Any thoughts?
Things relating to the sine and cosine function?
Yeah, not quite. I mean, related, but not the way you're thinking of. What about the eigenvalues? Any thoughts? If they're complex eigenvalues with magnitude 1, you end up with a cyclical pattern. Can you imagine why that's true?
Yeah, because like with even and odd, it'll fluctuate. And
yeah, you get a rotation. Exactly, you get a rotation. So that's what's going on there. So all kinds of models doing weird things. Okay, now comes the next one, and this is a really cool one because most of you have heard of it, and none of you have seen it this way. Okay, and this is Fibonacci, and Fibonacci proposed it with rabbits. What are rabbits famous for doing, by the way?
Mating.
Reproducing a lot.
Reproducing. Okay, so that's why Fibonacci did it with rabbits. Although I think he did it in, I don't know, Italian or whatever, and I don't know the Italian word for rabbits, but however Fibonacci said it. So here's the way it was worded. Basically, suppose female rabbits, okay, all have exactly one baby rabbit forever after they are 2 months old. So we're doing a big assumption that rabbits never die, which is not true. But to make life a little easier, that's what Fibonacci did. Okay. At the beginning, there is only one female rabbit in existence. Okay. Doesn't mean there's no male rabbits, by the way. How many rabbits will there be after 1, 2, 3, 4, 5, all the way to n months? In fact, I'll even pop in 0 just so that we can put that in. It'll look more like Fibonacci. Any questions on the question? All right, so let's just do the first few easily. How many after 0 months?
1,
Yeah, this is 1, because I told you there's only one female rabbit right now. How many after a month?
2,
Oh, I should say there's one baby female rabbit. How many after 1 month? It's not 2.
Still 1.
It's still 1 because that baby is now a child instead of a baby. Do you see? Now, children don't have babies. Any questions on that? Okay. So I'm answering the question. I'm going to answer the first 5, but then n is going to be harder. How many after 2 months?
2.
Yeah. Why are they going to be 2?
Because it says after they are 2 months old, they have 1.
Exactly. So there's one that's sitting there that just became 2 months old, just had a baby. Any questions on that? Okay. How many after 3 months?
Still 2.
No, remember there's that original rabbit is not a baby.
So 3.
There's 3, right? Because there's one baby and one adult. Okay, that's 3. Now you might look at this and say 1, 2, 3, 1, 2, 3. Do you think it'll be 4, 5?
No.
Absolutely not. Okay, how many will there be after 4 months?
6.
There won't be 6. It's a good try.
And 5.
It's going to be 5. And here's the reason. So this is the way we want to look at it. So the way we get this 5 is we can say, well, there are 3 rabbits, right? But 2 months before that 5, there were 2 rabbits. So those 2 rabbits here are going to have a baby. So there's going to be 2 babies from 3 rabbits that we started with, and that's 5 rabbits now. How many are going to be on the next month? So month 5 now. All right. If you don't see it, then maybe I'll go through it again. Yeah.
8. Yeah.
Because again, 2 months before that 8, there were 3 rabbits. Those 3 rabbits are all mature enough to have a baby. So it's going to be 3 babies in addition to the 5 rabbits we had the step before this. So that's an 8. How many are there going to be in the next month, month 6?
13.
Any questions on that? Let's do one more. How many are there going to be in the next month?
21.
21.
21. All right. All of a sudden, it's not counting by ones anymore. You notice that? Okay, now comes the hard part. How many are there going to be after n months? Any questions on that? So how many babies will there be after n months? Okay. So if I told you after, 1,000 months, we don't want to do this for 1,000 times, do you?
No.
No. I have better things to do with my life than do that. How about you? Okay, so that's not going to be the strategy. Instead, what we're going to do is we're going to see if we can write what's going on in general first. So what's going to happen in general? How did I get this 21?
Added 8 and 13.
Right. So I can say that I got to, and let me write this down as an equation. I got that A sub n plus 1, or 2 actually, was equal to A sub n plus 1 plus A sub n. Do you agree with that?
Yes.
Okay. So, if I wanted to, but we're not going to do it this way because it's linear algebra class. This is not a computer programming class. But those of you who've had coding theory, could you code this?
Yeah.
Yeah, you would do it with a recursive function, right? But we don't want to do it that way. And if I asked you for the millionth one, do you know what would happen if you tried to code it?
You'd overheat your computer.
Exactly. It turns out that when you do recursive algorithms with this kind of double recursive function, then it's 2 to the nth is what it's going to be able to, it's going to RAM up, put in RAM. And 2 to the millionth is not okay with the computer. 2 to the 10th is fine. 2 to the millionth is not fine. So you just kill the computer. So that didn't work. On the other hand, and this is totally tricky. Ready for the tricky? Something that you probably would never think to do. But turns out you have to do it. And that is A sub n plus 1 equals A sub n plus 1. If you don't believe that, you don't belong in this class. Do you all believe that that's true?
Yeah.
Okay. Typically, though, we do the following. We write that one first. Any questions on that? I'm going to write a little more than that just to add some more nonsense. Plus 0 times A sub n. Do you all agree that's okay?
Yes.
Why did I do what I just did, which seems like a total waste of time?
Because it's in the right form for what we did before.
Yeah, now we have a matrix. Do you see that? Now we have and let me pop up our definition since we had it. We have a discrete dynamical system. Do you see that? Where we have X and Y are now the AN plus 1 and AN plus 2. So I can rewrite this as follows. And I'll write it with X and Y because it's just easier to type. I can write down, what is the matrix? What do I have? And I know that this is going to sound a little weird because we have an plus 1. So this is the next step, right? So you usually put it in the exact opposite order. Does that make sense? Usually put an first. But I did this because that's how we counted before. So it's going to be 0, 1, 1, 1. Times xy. And that'll give us our next step. Any questions on that? Okay, what do I do now?
Don't we have to set it equal to something?
Well, if I want the nth month, what do I have to do?
Oh, raise our matrix to the nth power.
Yeah. Now, how do I raise a matrix to an nth power nicely?
You can do find a
Diagonalization.
I need to diagonalize this matrix. Exactly. So let's diagonalize our matrix. What's the first step to diagonalize the matrix?
Find the eigenvalues.
Yeah, we need to find the eigenvalues. How do we find the eigenvalues?
We have a formula for a 2x2.
Yep, and let's do it. By the way, can we just say 1 is an eigenvalue because that was the theorem we had earlier?
No.
Yeah. Wait, no, we can't because this is not a Markov matrix.
Right, it's not a Markov matrix. If you add the columns, you don't get 1. The first one works, second one doesn't. Okay, but what you can do, which isn't that bad, is we can write down using our formula is lambda squared and then remember how it goes next? Minus
the trace of a.
What's the trace?
1. -1.
Well, the trace is 1, so it's -1. Okay, or minus lambda if you want. And then
plus the determinant.
And what's the determinant?
-1.
So -1. Set that equal to what?
0.
0. Okay, this isn't so beautiful, but at least it's not complex, right? How do you solve this?
Well, I would use symbol lab just because I'm lazy, but you could also.
Oh, come on. I think it's harder to use. I think it's harder to use.
Yeah, it's in this individual example, it's probably harder to use symbol lab, but yeah, you would just factor it.
No, this doesn't factor.
It doesn't factor? Oh.
No. Yeah, if you could think of two numbers that multiply to -1 and add to -1, good luck.
Quadratic formula.
Yeah, quadratic formula, but the numbers aren't big, or the numbers are all tiny, right? So let's do it. I think it's worth it. And I'm sitting there typing it. Typing is like the hardest part of the whole thing. So it's -b, which is 1, and then it's plus or minus. I think I can go plus minus. It'll do it for me. Yep. Plus or minus the square root of b squared minus 4ac, which is 1 minus 4 minus -4, which is 5. all over 2. 2a, which is just 2. Come on, you got to admit that's easier than Symbolab, isn't it?
Yeah, but I haven't used the quadratic formula in like forever.
But these numbers are easy. So there's our lambda. Just to let you know, by the way, the 1 plus the square root of 5 over 2, do you think that's an important number?
I'm going to say yes because you asked.
Yeah. Have you heard of the magic ratio?
No.
Okay, this is called the magic ratio. And for some reason, no one quite understands why it comes up everywhere. So they've done psychological tests of like, what's the most beautiful picture? And they do, larger widths and smaller widths and larger heights. And they found out that everyone likes the magic ratio. Isn't that cool? And do you know why everyone likes the magic ratio? Right? Those picture frames are almost always the same dimensions, right? In terms of the ratio. Do you know why?
Our brains just like some symmetry.
Well, there's lots of symmetry, but what do our brains like? No, they like faces. And that's the ratio of our faces. So we like it. It's all over the place, this magic ratio. It comes up in so many different applications. So I figured I'd give you others too, besides Fibonacci. All right, so there's our lambda. Okay, it's kind of messy, but it is what it is, right? Then what do we have to do?
Find our eigenvectors.
Yeah, so now we got to find our eigenvectors. So we're going to take our matrix. And then we're going to have to subtract lambda I, right? So, and you can go either direction. I think it's easier in this case to do lambda I minus A. So I'll put some minuses on these ones. Then we don't have to play around with the magic ratio. And then again, I'm going to use 1 plus root 5 over 2. Actually, I don't need the second column at all, the second row. Remember that it's guaranteed that the determinant must be 0. So there we have it. And now it's easy. So what we do is we make sure that x is equal to, or that 1 plus root 5 over 2x minus y equals 0, right? So let x be 1 and y be 1 plus root 5 over 2. So we get one comma 1 plus root 5 over 2. Any questions on that? Okay, I don't think I'm going to finish the whole thing, but the point is this could be done. So then we do the same thing and we plug in a lambda equals 1 minus root 5 over 2 and get the second eigenvector, right? And then once we have those, you can normalize it by dividing by the magnitude, take the transpose, and then you'll end up with our correct matrix. And by the way, what's our D?
It's our eigenvalues in the diagonal.
Yeah, so D is going to be 1 plus root 5 over 2, 0. Zero, 1 minus root 5 over 2. That's going to be the D. And hopefully you all know how to do, if I said that you want to do 1,000 of these, what's D to the 1,000th?
It's going to be our diagonal components raised to the 1,000th power.
Yeah. We just put a parenthesis. Let me. There we go. Okay. Actually, I want N, because I asked you to find N. And then the same thing over here with the 1 minus. So that's our D to the N. Then you just multiply it by the P and the P inverse. And that will give you the formula to find out what the N Fibonacci number is. Any questions on that? And by the way, it looks ridiculous because it doesn't look like an integer at all, does it? When you take the sucker to the N. When you're all done, are you going to get integers?
No.
One more guess?
Yes.
Yeah, we're finding the Fibonacci numbers. Right? We're adding the last two numbers each time. You're never going to get fractions. It's actually a proof that you get integers. You know, that's the proof. Any questions on this? Kind of cool. Did Fibonacci comes up other than like these fictitious rabbits?
Pine cones.
Yep, pine cones. Okay, pine cones have Fibonacci patterns. Cool thing is, turns out so does the northern ice range of Mars. So you can trust me on that.
The frozen CO2.
Yeah, that frozen. I don't know if it's CO2 or H2O, but frozen something. At the North Pole of Mars. Yeah, it might be CO2, but there's a northern frozen area, and it's a spiral, and it's got that Fibonacci pattern. It's kind of cool. So since Mars was big in our news lately. So I want to move on because we only have 15 minutes or so, 16 minutes, and we have something very important. And this is a review of third quarter. Don't you hate when I do that to you? When I assume that you remember everything that you ever learned in calculus? And this is the definition of E to a matrix A. And that is E to the A is defined by the power series. So do you all remember that the power series for y equals e to the x is a summation of x to the n over n factorial? You can at least pretend you remember that.
Yeah.
Okay, it was the most important power series there is. Okay, on a scale of 1 to 10 in importance, that's a 10. Probably the next most important is a 5, just to give you an idea how important e to the x is. So e to the a, we define as a summation of k equals 0 to infinity of a to the k over k factorial. Now, does that make sense? Can you take a to a k power?
Yes.
Can you divide a matrix by a number?
Yes.
Yes.
Yeah. Can you add a bunch of matrices?
Yes.
Then this is defined. Okay. Because without this definition, if I just said, what is e to the a, you just go, you know what I mean? And you can't do what you did in pre-calculus, where you just kind of let it be whole numbers. doesn't work. And you draw a picture and you say connect the dots. I don't know if you remember doing that in pre-calc. and then the professor just said, hey, there's e to the x or 2 to the x or whatever. And he was able to draw a picture and you all believed her or him, right? With matrices, you can't even draw a picture. There's no graph if A is a matrix. So this is the definition. Do you think this ever comes up?
Yeah.
In a big way. Okay, so let's do an example. Let's find e to the 260 -1. Okay, I realized I was only gonna have so much time, so I tried to pick an easy one. What do we do? What's the first thing we have to do?
Put a to the k.
Yeah, use it. Well, put all the other stuff with the definition. So I'm going to copy the definitions because typing is a pain in the computer. Start with the definition. Got it? Then I can copy this matrix. And there's our definition, right? Any questions on that? All right. The problem with this, even with the computer, is good luck. So what are we going to have to do to find this 260 -1 to the k nicely?
Diagonalize.
Yeah, I get to find the eigenvalues. Okay, the hint is the eigenvalues are very easy. What are the eigenvalues? Hint is very easy.
Two and 1.
2 and -1, right? So we have a triangular matrix. When you have a triangular matrix, the eigenvalues are just the diagonal elements. Again, I gave you an easy one because we don't have that much time left. Okay, and I knew we wouldn't. So what we can say, and I'm going to jump to the chase, D. Let's just do this. So D is going to be 2, 0, 0, -1. Any questions so far? Because our eigenvalues are 2 and -1. By the way, why did I write D before I even how do I know this is diagonalizable? Because not all matrices are diagonalizable.
The determinant wasn't 0.
That doesn't quite do it.
We get the correct number of eigenvectors.
Yeah. I have a 2-dimensional space, and I have eigenvalues, not vectors, though, right? And I have 2 eigenvalues. So if I have 2 eigenvalues in a 2-dimensional space, I'm good. That was the theorem we had. So we know that it is diagonalizable, so that means I have a shot at this. Any questions on that? Okay, it means I can do it as long as I don't make a mistake. All right, so what do we have to find now?
Our eigenvectors.
Yeah, so now we find the eigenvectors. So let's do that. So how do we find the eigenvectors? We take this matrix again. And then we subtract lambda I, right? So I'm going to subtract lambda I. In this case, my first eigenvalue is 2, right? So that means I subtract 2, which is nice. Gone. So if I subtract 2, then I can just write it like that. Wait, did I lose my, I still have 6. And then that's a 0. Could always let the bottom row be 0, as long as the top row is not 0. Any questions on that? So what's my value?
One zero.
Yeah, 1 0. Nice and easy. So V is sub 2 is equal to 1 0. Okay. Now I do the same thing, right? So now I take the eigenvalue of -1. I take the 2, 6, 0, -1, and I subtract -1. And when I do that, I get a 3, 6. So V sub -1 is equal to
-2, 1.
We could write -2, 1, but I'm going to write it differently. I'm going to write it as -2 over the square root of 5 and then 1 over root 5. Why did I do that? Why did I make it so ugly looking? There's a very important reason. Can anyone tell me? Here's the hint. It starts with an O.
Orthogonality.
Yeah.
Yeah. I want to orthogonally diagonalize this matrix. Does that make sense? So how does orthogonal diagonalization work? So I have my P. Do I put the P first or I put the P inverse first? Do you remember?
It's P first.
It's P inverse, isn't it? I don't know. Which is it? Let me check my notes.
Yeah, so I'll let you look. So A equals, so in particular, we can write down.
It's P first.
Yep. We can write down that e to the 260 -1 is equal to, so now I have my, oh, I just lost it. Didn't want it there. I want it here. There we go. So now instead of 260 -1, I have my P, which is going to be 1, and then -2 over root 5. 0, and then 1 over root 5. And then times our diagonal to the k. Diagonal is just 2, 0, 0, negative 1. But the to the k can go away now. And get put into the diagonal. And then, what do I write for my third matrix?
P inverse.
And what's P inverse?
P transpose.
Yeah, that was the whole point of putting these messy numbers in. Is now I can transpose. Transpose is really easy because I just switch the diagonals. And there's my e to the 2, 6, 0, negative 1. Any questions? Any questions on this process? And for any k, this is not that hard to compute, right? So if I wanted up to, you know, maybe the 5th degree approximation, then I can do that pretty easily, especially the computer. Any questions? Okay, so I don't have time to do the whole solution, but we can look at this. What if you wanted to solve x prime of t equals 2x plus 6y, and y prime of t equals negative y, x of 0 is 1, and y of 0 is 3? What do we do?
I'm plugging our values.
Plug in the values, but I want to make it a matrix equation. Remember, there's linear algebra, don't forget. So we make this a matrix equation. So let's make this a matrix equation, and it'll all be beautiful. And again, I want to time to finish the problem, but at least I can start it. So the first thing is we have x prime. Let's just write xy prime equals. And now what's our matrix?
Two,
Mm-hmm.
6, 0, negative 1.
Have you seen this before?
The one we just did.
Exactly. Times xy. Well, that's the same thing as writing down y prime equals ay. Does that make sense? Or say v prime equals av. Well, if you have v prime equals av, what's the solution to v prime equals av? The solution is e to the a. But not quite. There's one little extra. So we're going to have xy is going to be e to the 2, 6, 0, negative 1. But why is it not just that? Think calculus. I just integrated. What did I forget to do? Plus c. But it's not plus c, it's plus c1 and c2.
So you have to add on a constant vector then. And it'll be
Exactly.
the
Does
integration.
that make
Okay.
sense? Okay, again, we're out of time, but I'll tell you what you do next because we've already done most of it. I'll even do part of it. Is we've done the e to the power. I know it's a mess, but believe it or not, it's less messy than e to a power because e to the power doesn't work in a calculator. That won't let me do it. So we take e to this, we take the summation of this beautiful matrix and then plus C1, C2. What haven't I used yet? Let's go back to the problem.
Are x of 0 and y of 0.
And what's that going to get us?
Are C1 and C2.
Exactly. That'll give you your C1, C2 if you plug in 0. Oh, do you know what I forgot to do? T. Got to stick a T there, right? And then if you plug in 0 for T, you get C1 and C2. And I'm out of time, so I'm going to stop the share. I don't want to, especially on a Friday, that's not cool. So I'm going to stop the recording.